This is the problem about the flexor, and the problem reads: a man holds a 178 Newton ball in his hand. By the way, that's in the neighborhood of like 40 pounds, so quite a bit. With the forearm horizontal, see the drawing, he can support the ball in this position because of the flexor muscle force M, which is applied perpendicular to the forearm. The forearm weighs 22 newtons. It's in the neighborhood of 5 pounds. It makes sense. I guess we could estimate our forearm to be about 5 pounds. And has a center of gravity as indicated. Find A, the magnitude of M, and B, the magnitude and direction of the force applied by the upper arm bone to the forearm at the elbow. I'm going to start out with actually drawing that last piece of information down here because I don't have it in a drawing. So they say that there's some force at the elbow joint by the upper arm bone, and I may want to call it FA, force by the arm here, and that's just the tension in the bone itself that is holding the elbow joint. And I don't know how long it is, and I don't know in which direction it points. I'm just assuming that, yeah, the arm bone in fact is pulling up on the elbow joint rather than pushing down. So, okay, well, let's get started. Let's see what we got. We have the force, that is the weight of the lower arm itself, and the weight of the ball, and we're supposed to figure out what the flexor muscle's force is, and we're supposed to figure out what the force is that is applied by the upper arm bone. And then looks like we have all the lever arms given, and it's in equilibrium so that the sum of the torques come out to 0. And now I'm gonna choose arbitrarily. I can choose arbitrarily where my rotational axis is. I could choose it here, 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 or here. I may choose one where it's convenient, so I will choose this one here because I don't know what F is. But if I choose my rotational axis here, then my lever arm to this force here, to this unknown force here, is 0, and therefore it's not going to figure into my first equation. And then the only unknown that will pop up there is the force M. So I'm going to have M times the lever arm, this one here, that is the 0.051 meters, 5.1 centimeters. So I may want to call this LF because it goes to the flexor muscle. And then I add to that the weight here at the lower arm. I might want to call it WL. Let's see, even the problem is that they call it the they called it the forearm. I call it the lower arm so that my indices are not confusing each other. So the weight of the lower arm times the lever arm, and that is of course the total here. So these, I think that's 14 centimeters, 0.14 meters, times the L, the lever here of the lower arm, and then plus the weight of the ball times the lever arm of the ball, which is the total from here to here, so the 0.33 meters. That's a little over a foot. That makes sense too if we look at our arm. Actually, it looks a little bit longer. That must be a small arm here. Okay, anyway, and I equal it to 0. And now the only unknown that I have is that force M here, so I can solve for it. And I want to keep in mind that this weight here is negative. So that's actually negative 22 newtons. And this force here, this weight here, is also negative. So that one is negative 178 newtons, and all my lever arms are positive numbers because my rotational axis, my conveniently chosen otherwise arbitrary rotational axis, is on the very left, so all the lever arms come out to be positive. And then I do the algebra and I solve for M, which is basically add all this here and on the left hand side that would be a negative and comes out to a positive. On the right hand side, divide by a positive number, so overall the magnitude of the flexor muscle comes out to a positive number, and of course it's going to be in newtons because the weights are in newtons and the lever arms with their meters are canceling when you divide by the meter here. Okay, this is actually part A, and then part B is figuring out what this force is here, and there are several ways of doing it. You know, again, shift the rotational axis to here and you only have this unknown, or put it anywhere, and with this one being known now we can figure that out. Or I believe the easiest one is to say that all the forces need to balance each other, so the original Newton's second law applies just about the forces, which is Fa plus m plus the weight of the lower arm plus the weight of the ball, and that equals 0. And again, this one here and this one here, these two are negative on the left hand side, they become positive on the right, and then subtract m from that and you come up with what the force A is of the upper arm. And I can just give away that you will come up indeed that it's a positive number, so positive something newtons, and that would validate my original vector arrow that points up. And as I said, that was just a guess, but it kind of looks like that the upper arm bone should be pulling on the elbow joint rather than pushing. This problem is about the bowling ball, and it reads: a bowling ball encounters a 0.760 meter vertical rise on the way back to the ball rack, as the drawing illustrates. Ignore frictional losses and assume that the mass of the ball is distributed uniformly. The translational speed of the ball is 3.50 meters per second. At the bottom of the rise, find the translational speed at the top. In here it says the mass of the ball is distributed uniformly, which means we're looking at a solid sphere with the density the same everywhere, and that's what they mean by that. So we just apply the moment of inertia for a solid sphere. Anyway, also in this problem I left this box empty here just to show that how do I actually develop the number of variables, or which variables I put in this box here. You have seen me do that in the past. That's already set up. In this particular chapter, we come across quite a few concepts on angular momentum, rotational energy, moment of inertia, center of gravity, torque, and so on. And so there are quite a few variables in here, so I just want to show you, this is how I set up the box. Okay, anyway, this one is actually in rotational energy, so that's what we should have, that the energy here, which is kinetic energy, translational kinetic energy, and the rotational energy, this is important here, as it goes up, become the potential energy, of course, because of the rise here, and therefore some of the kinetic energy is gone and some of the rotational energy is gone, has been converted into potential energy. And that's where I should start out with, that I write before the rise I have the initial kinetic energy, that was supposed to be an I, and the initial rotational energy, again an I, and then after the rise, and of course I have the potential energy down here is 0 if I choose my 0 line to be right here. And then after the rise, it's going to be the final kinetic energy plus the rotational energy plus the potential energy.